Hello everybody. Let us start with the today's lecture on crystal plasticity. So few parts I have covered in the last lectures. Now we will try to wind up the last part of the crystal plasticity. So here we will focus on the few things like first is the yield criteria, flow rule, and finally the hardening rule. Basically we have seen that in continuum plasticity we try to define that what may be the yield criteria we can follow, and based on that we have developed the von Mises yield functional form for a specific material, and then we use the different flow rule to predict the plastic behavior of the materials, and also we use the different hardening rule also to explain the phenomena of the increment of the strain level after the first yield point. So there are different constitutive relations exist, and we will try to using that relationship, and we explain the different continuum plasticity model. But in crystal plasticity it may not be very straightforward to defining the yield criteria, flow rule, and the hardening rule, because in this case that at the microscopic level the behavior of the plastic deformation for a single crystal is more complicated. So there maybe the several theory exist, but we will try to overview on that, and we will try to get the basic understanding on the topic of the yield criteria, flow rule, and the hardening rule in case of crystal plasticity, or specifically when you try to focus on the single crystal plastic deformation behavior. Or finally we will try to find out in case of polycrystal form how we can use this theory in some aggregate form, or we will try to explain the different theory behind the polycrystalline plastic deformation. So to do that, first why we will try to understand the crystal plasticity, and why is it necessary, and what is the bottom line theory exist to understand the plastic behavior of single crystal structure. So one thing is that behavior at the macro level is basically plastic anisotropy is controlled by features at the macroscopic level, and in this case crystals and their dislocation behavior or dislocation exists within the crystal structure, need to analyze that. But of course here we can see that at the macro level, even here also the anisotropic plastic behavior exists. Second point is that crystal plasticity or maybe polycrystal plasticity provides a theory that actually links the constitutive response to the key microstructural features to model the plastic, specifically the plastic anisotropy. So anisotropy of single crystal properties, actually it is related to the crystal structure and the slip system, and at the same time we need to consider the crystallographic structure into account to explain the anisotropic plastic behavior when you try to focus on the single crystal deformation behavior. So theoretical description on this plasticity model, first we will try to focus on the single crystal. So here the deformation mode, we have discussed the deformation mode in terms of the slip we have explained, and the slip phenomena also we explained in case of single crystal structure by defining the single slip plane and the several slip directions. So one such critical amount of the shear stress that is required to initiate the yielding, that is called critical resolve shear stress. So we have already explained that how we can estimate the critical resolve shear stress for a specific crystal structure. But another point is that, so when we try to explain the plastic deformation by the slip system or by the mechanism of the slip in a single crystal structure, So it is actually associated with the reorientation of the single crystal. So there may be some rotation of the crystals, and that can be, after rotation they can orient it one specific direction, and that is called specifically structure. So structure is having very important phenomena to analyze the crystal plasticity, and that actually brings the complexity is the plasticity theory, and which is different from the continuum plasticity theory in this case. So once we done for the single theory or application or analysis of the crystal plasticity for single crystal, then we will try to estimate or we try to link with the aggregate of the crystals, for example in case of polycrystals. So average aggregate over the stress and strain can be done in case of the polycrystals, and that polycrystalline structure, the display of the orientation or structures actually better link or better explain with the pole figures, but we will not be doing into much details on the pole figures. In this case, we will try to understand the basic theory behind the crystal plasticity. So to do that, or to enter into the actual topic, probably we can look into the review work so far we have done related to crystal plasticity. First, we started with the crystal imperfections or crystal defects. We will try to identify the broad category of the crystal defects, the point defects, line defects, and the surface defects. So here we have explained the crystal plasticity in most of the cases in terms of the line defects, that means in terms of the dislocations. Then we have tried to estimate the dislocation geometry to basic elements, screw dislocation and edge dislocation, and what is the associated amount of energy with the screw and edge dislocation that we have estimated. Next, we discussed on the dislocation motion and the slip system for a specific crystal structure, simple crystal structure. For example, we consider the FCC, BCC and HCP crystal structure, what are the slip system exist, all these simple materials. Then we have defined the slip system, that means it constitutes on defining the slip plane as well as the direction, slip direction on the specified slip plane, that constitute actually the slip system of a specific crystal structure. Then we discuss the dislocation source by using the Frank-Read source of dislocation generation. With that mechanism, we have explained with the further straining or plastic deformation of the crystals, there is a generation of the dislocations, and that actually increases the dislocation density of a specific sample, that we have explained. Next, we have tried to define the resolved shear stress, and from the resolved shear stress, the critical value of the resolved shear stress, that actually starts the initiation of the yielding, that is called critically resolved shear stress, that we have evaluated for the simple crystal structures. And then we have derived the stress field associated to the dislocation. Individually, we consider the stress field associated with the screw dislocation and edge dislocation, and finally how these stress fields are interacting in the presence of the another dislocation of opposite sign, that we have explained. And then we explain the dissociation of the dislocation, maybe full dislocation, how it can be dissociated into two partials, or maybe dislocation reaction in terms of the two partial dislocation can form in the another dislocation by looking into that vector summation of the partials, or looking into by analyzing the energy level changes during that reactions. We have discussed the reaction of the dislocations, and finally we discussed dislocation mechanics, different mechanics associated with the dislocation, for example dislocation piles up, dislocation intersections, cross slip, all these phenomena we have tried to explain in terms of the dislocation. And overall, if we see that all discussion has been done with the two basic reference points. One is that in terms of either edge dislocations or in terms of screw dislocation, but practically this is the very basic elemental things, the edge and screw dislocation, and in practical there may be the combination of both the components must be there. Now we come to the actual part of this lecture, that is the classical plasticity, how we can explain these things. Actually, the most feasible experimental technique we generally consider, that is either uniaxial tension or compression, and from that we get the data itself and we compare with the theoretical prediction of the single crystal structure or maybe polycrystalline structure. Now, few facts to analyze the classical plasticity theory or associated with that. One point is that at room temperature, the major source of plastic deformation is the dislocation motion through the crystal lattice. So we need to understand the dislocation motion to understand the plastic deformation in the single crystal structure. Second point is that dislocation motion, or maybe sometimes we can call dislocation glide, basically occurs specifically on certain crystal plane and in certain crystallographic directions. Third point is that crystal structure of metals actually not altered by the plastic flow, or maybe we can say by the dislocation motion. What are the volume changes associated with the plastic flow are negligible in this case. So this is the typical key facts to remember when you try to enter into the analyzing of the basic crystal plasticity theory. Now, what are the mechanism of the plastic deformation? So first is the plastic deformation. Basically, we have several times we have discussed that plastic deformation can occur by many mechanisms, but one of these is the slip mechanism, which is most important here, and we are trying to analyze all these phenomena based on this slip mechanism. In the crystalline materials, slip involves the motion of the dislocation on a specific slip plane, and we have already defined that creates one single step that actually associated with the Burgers vector, or we represents this thing, the motion or maybe slip in terms of the Burgers vector. Third point is the slip is caused by the shear stress. So at the level of the slip plane, but since purely hydrostatic state of the stress cannot cause the slip, since slip occurs only by the shear stresses. This is very important phenomenon to consider, that purely hydrostatic state of the state does not influence the slip mechanism in this case. Next point is that if slip occurs only part of the plane, definitely that actually creates a boundary between the slip and unslip portions, and that actually called in physically, that is called the dislocations. So under any given external condition, slip will be initiated when on a particular slip plane the amount of the stress or shear stress exists certain value, that is called the critical resolved shear stress. When it is reached, then only slip will be initiated. So this is the key fact we have already discussed. Just I am reviewing on this fact to analyze the mechanism of the crystal plasticity. So, but in this one point is that for a slip in a polycrystalline material, they require the 5 independent slip system. So here the significant term is the 5 here, that we can say for a polycrystalline material actually we need to define 5 independent slip systems. So why this number is important? Because so far we have discussed the slip occurs only one specified slip plane and in one direction, but we have not discussed what is the consequence, or whether is there at any time whether several slip system is active or not, that we have not discussed. But polycrystalline material, it is required at least the 5 independent slip system is required. We'll try to explain, or we'll try to mathematically prove that why 5 independent slip system is required to initiate the slip in case of polycrystalline material. Then that means at one time a number of slip system is important here. To look into that aspect, if we see that materials which are ductile in single crystalline form, they may not be the ductile in polycrystalline form, because in polycrystalline form there may be at the same time is the initiation of the several slip planes or initiation of the several independent slip system. CCP crystal, that means cubic closed packed crystals, have excellent ductility because of the less number of slip system probably active in this case. But at high temperature, more slip system may become active, and hence polycrystalline materials actually which is brittle at the low temperature, probably they may ductile at high temperatures. And just the existence of a slip system does not guarantee that slip will occur, because at the same time slip is the competitive against other processes like twinning and fracture. If the stress to cause the slip is very high, probably critically resolved shear stress is very high, then fracture may occur before slip. It is like the brittle ceramics. For example, even in continuum mechanics also we have observed that brittle fracture actually occurs without the much deformation in the much plastic deformation. For example, in glass can be considered as a brittle material. So when we apply the load, so almost no deformation, it simply breaks. So directly with the application of the load, it reaches to the fracture point. So similar phenomena can also be observed in this case when you try to explain the crystal slip system in case of the single crystal structure. Now, like continuum mechanics also, if we see how the slip occurs, that strain hardening or work hardening, actually this mechanism also active by the dislocations interacting with each other when there exist some barriers which impede their motions through the crystal lattice. So in strain hardening for the single crystal structure, when there is a resistance to the dislocation motion, that actually raise the further stress level. So that is because of the strain hardening mechanism exists for this particular material. So definitely dislocation density increases dramatically during the deformation. So once it starts the yielding point with the further straining or further plastic straining of the material, there is a generation of the multiple dislocations. So practically in a specific sample, there is an increment of the dislocation density. But presence of the precipitate particles, foreign atoms actually acts as a barrier which results in the dislocation multiplications, or that actually that barriers resist the dislocation motion as well. Finally, the dislocation piles up if there exist some barriers or at a specific barrier, that actually produce a back stress which actually improves the level of the stress with the further straining of the material. So basically in single crystal also the strain hardening mechanism exists, and that actually explains by the resistance with the dislocation motions in presence of certain barriers. This is the basic phenomena of the strain hardening in case of the single crystal structure. Now, if we look into the plastic deformation of single crystal structure, we can see graphically that it's a graph of the shear stress and shear strain, and we can define the deformation zone into three parts: stage 1, stage 2 and stage 3. If we see that in stage 1, actually that is called the easy gliding. So basically easy movement of the dislocation probably. So in this case starts with the slip occurs only one slip system at the very initial stage. So at this stage basically the dislocation density is very low. So probably the interaction of the dislocations chances here are also very low. So in this case, of course, with the further deformation of the plastic deformation of the material, there may not be much increment of the stress level due to the strain hardening mechanism. So basically crystal undergoes very little amount of the strain hardening in the very initial stage, or that means this is called in stage 1. In stage 2, if we see that strain hardening actually occurs very rapidly, that means there is an increment of the stress level within the small amount of the strain. So which physically indicates that the effect of strain hardening is very high in this case, because in this case actually slip occurs more than one set of planes, not is very confined to the only on single slip system. So there were multiple slip systems active on the stage 2, and that actually raised the level of the stress due to the effect of the strain hardening. At the consequently the same time, so if there is a strain hardening effect is very high in this case, so at the same time the dislocation density also improves, or dislocation density also increases at the second stage. In third stage, in this case, that plastic actually there is a decreasing rate of the strain hardening. So strain hardening rate is very low in the third stage, and the third stage it can be said that the reach shear stress is reached to the flow stress or maybe flow curve for the FCC single crystal structure. Now flow stress, what do we mean by flow stress? Actually the stress necessary to continue the deformation at any stage of the plastic strain. So probably at the stage 3 the amount of the stress can be considered as a flow stress, or it remains almost nearly constant, and where the strain hardening rate is very low. And if we see that the overall structure shear stress versus shear strain of a FCC single crystal, if we look into that, this is the approximation of the actual curve, and if we see the mechanism involved in the stage 1, basically we have divided into the 3 stages, stage 1, stage 2 and stage 3. Basically in the stage 1 there is a small increment of the stress level, stage 2 high increment of the stress level, and stage 3 probably less increment of the stress level, but is try to reach one specific steady state value that can be considered as a flow stress value in this case. And we explain this plastic deformation of the single crystal structure by considering the strain hardening mechanism, and in which cases the strain hardening mechanism is less or more. At the same time, at the very initial stage, the active slip system may be less, and if we go on further straining, then there may be the increment of the active slip system. The more number of slip system becomes active in the latter stage. Similarly, at the same consequence, we can say that dislocation density maybe at the very initial stage is very low, and gradually the dislocation density actually increases, and probably in certain point the dislocation density reaches the maximum point. Now, what may be the effect of the easy glide on this, specifically the plastic deformation of the FCC single crystal structure? So if we see that easy glide actually depends on its orientation, its perfection and the temperature. So all these parameters actually is significant on the easy glide, but high degree of the plastic perfection, a crystal perfection and low temperature actually promote more easy glide. So probably if presence of the dislocation is very less, that means it tends to the very perfect crystal, and very low temperature, probably the number of active slip system is very less, so that easy gliding is possible in that condition, or that condition actually promotes the easy glide. But if we see no easy glide is observed in BCC single crystal structure, because in BCC single crystal structure, if we see, or if we have analyzed what is the total number of slip system, theoretically it is having 48 number of slip system as compared to the FCC structure, because FCC structure is only 12 number of slip system. So since the presence of the several slip system in BCC crystal structure, so in this case there may not be the possibility of the easy gliding of the dislocation. Third point is that extensive easy glide is observed in tension test in case of the single crystal like HCP crystal structure, and which slip primarily on 00001 plane, that is basically basal plane. And so the most feasible reason in this case, the easy glide in case of HCP crystal structure, because even HCP is having very limited number of the slip system. So that is the reason for the easy gliding phenomena in case of HCP crystal structure. Now if we see the tensile deformation of FCC crystal structure, right hand side, if we look into that graphical form, the tensile strain versus tensile strain, here see that actually represents the stress versus strain curve, and if we see that there are two different directions. So 111, that is basically the body diagonal in that direction. So if we in that direction, if we apply the tensile load, the curve represents like that in the figure. I think this is the curve that represents the stress versus strain along 111 direction, and if we see the stress versus strain along 100 direction, that means along one of the axis, either x, y and z axis, if we apply the tensile load, we are getting the stress versus strain diagram. So if we see, there is a huge difference between the tensile behavior of a single crystal structure. So it depends actually which direction the load is acting. So there is a variation from the maximum possible variation to the minimum, probably. In this case, the huge variation observed. So but if we consider that polycrystalline material, so basically if we consider the randomly oriented grains having polycrystals, and that if we test for that polycrystal with the application of a load, then we are getting somehow in between that two directions, so some aggregate in between these two specific direction of the tensile axis. So this is the typical for aluminum single crystal structure or aluminum polycrystalline structure. We observe this type of tensile behavior. Now if we try to explain or if we analyze this phenomena, so in point wise, let us see. The first thing is that easy glide does not occur in FCC crystal oriented, so that slip occurs simultaneously on many slip systems. So here if we see for these specific crystals, we don't find the very easy glide very initial stage, because probably in this case the very initial stage a large number of slips or more than one slip system is active, so that strength level is high. Initial strain hardening rate is rapid and comparing with the polycrystal. So if we consider the individually direction, it is initial, at the very initial part it is comparable with the polycrystal form, but there is a variation, and how we can explain the variation, that can be better represented by if we represent the tensile axis, basic stereographic triangle with 1 0 0, 1 1 0 and 1 1 corners. What does it mean? Because in one single crystals, the tensile test can also be done at the several orientation or several direction. For example, if we see the two cases, one is the suppose 1 0 0 direction, we apply the tensile axis along 1 0 0 direction. That here if you see the 1 1 1 direction, so it is a variation. And if we do probably 1 0 0 1 1 1 and another 0, that is second one, that is 1 1 0 direction. That is 1 1 0 direction is the phase diagonal. So here if we construct the basic stereographic triangle representing that three directions at the three corners of the triangle. For example, one first corner probably 1 0 0, that represents the direction of one axis. 1 1 0, that is the direction of the face diagonal of a unit cell, that is the another corner of a triangle. And third one is the 1 1 1, that is the body diagonal direction of a cubic cell, that represents the third corner of the triangle. So within this triangle, if we consider there may be the variable direction. If we consider the tensile test, probably the stress strain diagram will be different, but how to capture or how to consider all these values of or specifically the tensile stress strain diagram that is oriented within that three axes, within that three corner of the triangle, so that we can represent in a contour plot of these things with the variable, with the variation, and probably we can use that data to represent, to correlate that stress strain diagram of a single crystal structure to the polycrystalline structure. We will try to see how it can vary. But basic philosophy is that first we need to fix the three corners of a triangle so that we can capture minimum to the maximum variable of the tensile strain that exists between these three directions, that is 1 0 0 that direction, 1 1 0 direction and 1 1 1 directions. But it is observed that for all orientations of FCC crystals within this triangle, the Schmidt factor for the slip higher for this specific 1 0 1 1 1 minus 1 is this specific slip system. We will try to explain that how this factor can be estimated theoretically, and to do that we can look into that how this triangle can be formed. See right hand side figure, if we see that one corner point represents the direction of the one axis of a unit cell. Second point is that direction actually represents the direction of the phase diagonal of a cubic unit cell, and third point represents the direction along the body diagonal of the cubic unit cell. So we are assuming that within these three directions there are several orientations, and that orientation can be represented in case of contour plot we can find out. So isocontour we can plot. So one contour probably represents the same value. So that is called isocontour in this case. So here in case of FCC crystal structure, we found that highest value of m is the Schmidt factor, so it is 0.5. So other is the, if you see that other variable, if you see in this case, that isocontour is the 0.45, 0.44, that kind of variation exists. So in between this variation, several orientation can be better represented by this basic triangle form. The highest value in this case, if we see, that is m equal to 0.5. So m equal to 0.5 corresponds to that. Suppose we consider resolved shear stress, and we define one slip plane here, that normal to the slip plane is represented by the direction n, and d is the slip direction, and suppose along the x axis, that is the tensile axis, applying the load. With this configuration, say we have defined lambda and phi. So we have already defined that how we can link the, how we can find out the resolved shear stress, or maybe how to find out the shear stress acting on the direction d to initiate the, or to initiate the slip of the crystals. So in this case, that lambda equal to 45 and phi equal to 45, probably it is maybe the optimum condition. So for this optimum conditions, here m equal to actually 5. So m is actually here defined cos lambda, and cos phi will come the later on how we can estimate this m, and is corresponding to 1 by root 2 into 1 by root 2, that means half, or this is the 0.5. So this is the maximum possible value of the m with the several orientation between the three axes of the triangle. So we can use the information and can find out the loading condition or stress strain diagram probably by looking into the m value. So let us see how we can use this m value to do the further analysis on that. Now we start with the slip process, but we have already discussed these things, but we try to represent the different to make the understand the plastic deformation in case of the single crystal structure. So slip, we understand the sliding of the planes of the atoms over one another during the deformation of the crystalline materials. Now when you try to do that, for the slip system, we define this Schmidt's law is this one, tau c, probably that tau c is the critical or resolved shear stress is linked with the tensile stress sigma x cos lambda cos phi, that slip direction normal to the slip plane, and this is the application of the load or tensile axis along which the direction the tensile stress is acting. So with this configuration, this is the Schmidt's law that we have already derived this law, and we can find out the actual value of the or critical value or resolved shear stress value on the to cause the slip of the atoms along the specified direction. Here it is, suppose the direction d. So when this tau c is the critically resolved shear stress value, then it starts the yielding of the material. Now we can find out in other way, that see here we can see the tau n d plus minus tau c we have considered here. So tau n d, we found out that in the stress system, this is the shear stress value, and another is the tau n d, the shear stress value, and sigma xs is the suppose normal stress value. So that we link in terms of the direction cosines L nx or L dx. So nx or dx, that link between the axis d and axis x, or between the axis n or axis x. So that with the definition of the direction cosines, we just simply linking the shear stress and the shear normal stress value. So here it is well defined that L dx or L nx, L dx probably we can cos lambda, and L nx is basically cos phi. So once we do that, then we can find out the sigma x equal to tau c by cos lambda cos phi, and basically tau plus minus tau c by mx. So plus minus we can consider the slip may occur. So when you consider the critically resolved shear stress, maybe forward or backward direction it may move depending upon the loading conditions. So that's why we consider either tensile or compressive. Accordingly, we can find out that plus and minus n we have considered. Now, if we see that sigma x, the normal stress value equal to tau c by some factor cos lambda cos phi. So that factor we can represent as mx, that is called the Schmidt factor, and we represent this as a cos lambda cos phi, that is the Schmidt factor in this case. So with this calculation, if you see the condition of the yielding under a general stress state, that can be written like that plus minus tau c, the critical resolved shear stress, is in terms of the state of the general state of the stress. So here we see the normal stress component and the shear stress component, and we find out all these components in terms of the direction cosines, and this is the general law of that. Now, when you try to predict the yielding under a general state of the stress, in this case probably we are not considering the lattice rotation during the tension. That is a one significant phenomena associated with the slip, because slip causes a gradual rotation or there may be the orientation change. So as the crystal is extended, the orientation of the tensile axis actually changes relative to the crystallographic elements. So that lattice rotation, actually with this theory we are neglecting the effect of the lattice rotation, but we will try to explain the linking of the lattice rotation with the plastic deformation, or with the slip system, or with the slip mechanism later on by just simply looking into the deformation, different plastic deformation theory. So here the significant point is that although we are predicting this simple yielding behavior in terms of the strain by linking into that general state of the stress, but lattice rotation we are not considering here. Now we can do further simplified calculation on that what is the amount of the strain produced by slip. So previously we tried to link the amount of the stress, now we try to link with the amount of the strain produced by the slip. So in this case, probably in the plastic deformation, always we try to predict the strain in terms of the incremental mode. So that incremental strain d epsilon xx, so that means along the x direction what is the normal strain component in the incremental form, we can find out by looking into the direction cosines between the different axes and what are the components of the strains, we can find out that. So here if we see that the three components are there, we link the epsilon nn, d epsilon dd and d gamma nd. So basically on the slip plane, two normal strain component and one is the shear strain component, and associated direction cosines, we can find out the incremental amount of the strain along the x axis, d sigma d epsilon xx in this case. Definitely this formula or this correlation is actually used to find the shape change in case of the small strain tensor, where the lattice rotation is basically negligible. Now, if the slip occurs in d directions and on the n plane the only strain term exists, d lambda nd, that actually defined internally when you try to explain the slip mechanism for a single crystal structure. So that occurs due to the amount of the shear stress and corresponding the amount of the shear strain, and that is the only shear strain associated with this. Then we can link the amount of the normal stress along x direction is only in terms of the shear stress component d lambda nd. Of course, all these cases we are representing in terms of the incremental form. Now, in the Schmidt notation, it is a d epsilon xx can also be represented like that. The factor cos lambda and cos phi, basically if we look into that, we represent the direction cosines here, and we can find out the simply m into d lambda. So where d lambda is the shear strain on the slip system. So only the shear strain component on the slip system d lambda, and we can represent the amount of the stress in terms of that Schmidt factor m and the corresponding incremental amount of the shear stress on the specific slip system. So we can do the further expression on the further component of the strains as like that, d epsilon yy, d epsilon zz in terms, all actually representing in terms of the that one constant value here, the amount of the shear strain d lambda, and we representing the all amount of the strain component in terms of the d lambda, that is actually happening during the plastic deformation of a single crystal structure. And we can use this correlation to find out the component externally to other different direction or in a x, y, z, the coordinate system in terms of the internal shear strain within the crystals itself. So after looking into this single crystal deformation behavior, but when you try to analyze the deformation behavior of the polycrystals, here we see that each grain is surrounded by others and deformed in such a way that the shape is compatible with the neighbors. So of course, when you try to analyze the deformation behavior in aggregate of the several grains at a time, then there may be the compatible issue with the respect to the surrounding neighbors. So you have to keep in mind this phenomena when you try to analyze the deformation behavior of the polycrystal. Second point is that slip on a single system within a grain may not satisfy the need of the compatibility. So we have to look into that, how we can satisfy with a better way the compatibility issue in case of the plastic deformation of polycrystals. Third point is the better agreement can also achieve if each grain undergoes the same amount of the shape change. That is the generally assumed by the in case of Taylor model. So we will try to mathematically represent this polycrystalline behavior with the application of the plastic deformation loading condition. So the strain with respect to an external axis, say x, y, z are fixed, and it is expressed in terms of the shear strain on the 12 slip system. So if we assume that in the 12 and specific now 12 slip system we consider, probably in case of FCC structure there exists the 12 slip system. So assume that in case of the FCC structure we consider the 12 slip system, and each slip system internally we define the amount of the shear strain is the gamma A, gamma B, or corresponding to the total 12 components is there. Now for each orientation of the grain, corresponding to the each orientation of the grain, we represents the amount of the normal stress with respect to that resolving factor, or probably that link the direction cosine with respect to the different axes. We see that state of the equations is like that: epsilon x equal to some resolving factor m, and that corresponding the all the different slip plane, the corresponding amount of the shear strain. So with the different orientation, we can possibly form that epsilon x, epsilon y, gamma yz, zx, xy. So two normal strain and the three shear strain component, we can represent the system of the equations. But here in this case, if we see, there is an absence of the z component, epsilon z. Probably that will come later on, but in this case, if we see that m is basically represents the resolving factor, and that resolving factor exactly comes from the nature of the direction cosines between the different axis systems. So that resolving factor actually product of the cosines of the angles between the slip element and the external axis. So m can be defined. Now with the 5 system of equation, you see there are 5 independent equations and in the system of the equations, but we have not considered the epsilon z in that equation. If we see that epsilon z is not considered here, because epsilon z is not an independent system, because compatibility conditions or maybe plastic incompressibility conditions, or if we assume there is no volumetric change, probably in this case the summation of all the strain component equal to 0. So from that condition, so epsilon z actually not independent equation, it is depends on the epsilon x and the epsilon y. So we have not considered the independent set of the equations as epsilon z. Now if we see there are 5 system of equations, solution of the equation requires at least 5 of the slip system must be active. So then if the material has the less than 5 independent slip system, then a polycrystalline material may have very limited ductility. But if we want to solve this equation, at least we need to define at least 5 of this slip system should be active. That's why at the very first few slides we already mentioned that 5 independent slip system is required. So this is the reason here we have tried to explain mathematically that 5 system of to solve the 5 system, the system of the equation, we need at least 5 system to be active. Now for an uniaxial tensile test, probably we can correlate the amount of the epsilon y, epsilon z in terms of the epsilon x, and or the shear strain component are 0. So with this information it is possible to solve the equation. So here I am not explaining how to solve this equation for a specific system, just to know the basic idea that system of equation can be solved in case of polycrystalline material when we consider the several slip systems active during the plastic deformation of that. But in FCC crystal, the deformation happens that on the 111 plane and specifically 110 in that slip system. But if we assume that various combination of the 5 of the 12 shear strain terms is the finite term, so out of the 12 slip system, probably we can assume that having the 5 combination is the finite. Then for each orientation of the crystal, we can select the combination with the lowest sum of the shear strain. So that is the summation of the I, that is represents the lowest sum of the shear strain, and out of the 12 system, 5 system is at least active. Now assume the shear stress to cause the slip may be the same for all the active systems. So amount of the shear stress to cause actually slip, that assume which is active for which is same for all the active system. Now definitely incremental work in terms of the per unit volume, that is the expanded, that unit volume expanded by the, so that is restricted the, or that is expanded by the slip. So that can be represented that dW equal to simply the amount of the work done. We can say that stress into strain. So that represents the amount of work done per unit volume. So stress into strain we represents, and this finally we can find out that T into d lambda. So in this case shear stress actually required for the slip of the ith slip system, and gamma is the shear strain on the specified slip strain, that is the representation of the tau I. Now summation of the d lambda I, so basically now we try to represent this, the 5 active slip strain, there is a small amount of the slip, and the summation of these things all having the equal effect, and we can say it is the summation of that is basically d lambda. Now from the external uniaxial tension we can find out the amount of the work done per unit volume, at the same time the normal stress into the normal strain, but here the in terms of the incremental volume d epsilon x here. Now equating the internal work done and the external work done, we can find out this correlation sigma x d sigma x and tau equal to dy. So tau dy basically it is a theoretical prediction. From the theory we can find out the amount of the incremental work per unit volume, this, and left hand side that actually represents that amount of the work done. When we step forward we can do the tensile test of a specimen. So with this correlation we can find out there is a m equal to d lambda by d epsilon x, the sigma x by tau. So that is actually one factor that is called Taylor factor, capital M. So in this case tension test can be randomly oriented FCC crystals, and orientation dependence of Taylor factor can be represents the amount of the that sigma x by tau in case of the FCC crystals. Now axisymmetric deformation is basically equivalent to tension test of a randomly oriented polycrystals. So if we see that similar way the orientation dependence of M, that is a factor, Taylor factor for the FCC that is undergoing the axisymmetric deformation, which is equivalent to the tension test for a randomly oriented polycrystals, and the 3 direction 1 0 0 1 1 0 and 1 1 1, the basic of the corner of a triangle. Now within that we are here it is possible to predict the distribution of the M in terms of the contour form, or isocontour can be seen from the figure that represents the distribution of the M. And if you see that, if you look into the distributions and specifically for FCC crystal structure, here we can find out the average value of M. M equal to here 3.067, and that is estimated the average value. So looking into the several possible orientation of the polycrystalline structure, which direction the stress is actually applied, or basically plastic deformation of the polycrystal occurs. So once we estimate the Taylor factor from the work done principle of the external or internal work, so we can predict that stress strain diagram, or we can link the stress strain diagram of the polycrystal form as with respect to the single crystal structure. Let us see how it helps to do that. Now if we look into that, the stress strain curve of randomly oriented polycrystal can be used to predict the shear stress as shear strain curve for a single crystal by simply knowing the Taylor factor, and that Taylor factor is the average. So when you compare or when you try to predict the stress strain diagram for a single crystal structure, we can use the average value of the Taylor factor for a specific crystal structure material. So that Taylor factor actually use this relation between the stress and strain in terms of the Taylor factor, normal stress, this is the strain, shear strain and the normal strain, and this is the normal stress versus shear stress in terms of the Taylor factor. So from right hand side figure also shows the same thing, that the polycrystalline behavior of polycrystalline, the stress versus strain figures is shown here, and corresponding the single crystal stress strain behavior, and this represents the polycrystal, and using this relation we can find out, or we can link between the stress strain behavior of the single crystal structure or stress strain behavior of the polycrystal structure. This is the one of the significant point, if it possible to find out for the specific crystal structure material, the Taylor factor, we can predict the stress strain behavior of the single crystal structure material as compared to the polycrystalline material by simply using the average value of the Taylor factor over the specific orientation of the in between the three different directions of a cubic unit cell. So with this, I can stop today with the analysis of the deformation of the polycrystalline behavior. Now next step we will try to focus on the constitutive models for the single crystal structure, or how the constitutive models can be done in case of the single crystal structure or polycrystalline structure, and which is almost in the similar direction what we discussed for the continuum plasticity. There we have seen that the different constitutive model can be formed, or different plasticity model can be formed based on the theory. Those similar, in the similar direction we can form in case of the single crystal structure. Thank you very much for your kind attention.